All right, section 4.2, we're going to talk about area, and in order to find area, we're going to sum things up. We're going to sum up smaller pieces of the area into one large area. So we're going to talk about summation to start. The notation here, we have the summation of a to the n, or I'm sorry, a sub n from I equals 1 to n. So we can define a certain number of terms here if we want to, the upper number. And I always steps by 1 each time. So it's an integer. It goes from 1 to 2 to 3 to 4 and on. Right. So as an example, if I have I squared and I'm summing up from I equals 1 to 4, that means 1 squared, then 2 squared, then 3 squared, then 4 squared. I'm adding all those up. And if I do that, I can just do the calculations. I get 30 here. All right. So here's some summation properties. And then here's some summation formulas. You don't need to memorize these. You can look these up if they come up. They're just useful for certain types of summations. We can use these formulas to figure out what they're going to be. And here's an example down here of a certain summation. We can distribute that I. We get I cubed plus I. And there's a formula for the summation of I cubed. And there's a formula for the summation of I. We can use those formulas to find 3080. Right. Really what we want to get to here today is talking about the area of a plane region. Right. And really what we're talking about there is the area underneath a curve, or between the curve and the x-axis itself. Right, so here we have, it looks like it is a parabola, negative x squared plus 5. So it's a quadratic, downward opening quadratic with a vertex at 0, 5. Right. Now if we wanted to approximate the area between this function and the x-axis, between x equals 0 and where we have the x-intercept out here, it would be at the square root of 5. Then we could approximate that by building rectangles. Right? So we don't get an exact. Well, we could build two different types of rectangles. Here I've chosen 4 just because they're easy to draw. All right? So I could use the upper sum, or I could use the lower sum. And you can see here I have my rectangles. The edges of my rectangles are defined by the same x-coordinates. So this goes from 0 to 0.5. This one also goes from 0 to 0.5. But here, the upper corner of my rectangle is defined by the height of the function. And here the lower, well, it's not the lower corner, but the corner of my function, the corner of my rectangle is defined by the lower point on the function. All right, so you can see I have a taller rectangle for the upper sum than I do for the lower sum. So clearly we can see that the upper sum is going to be an overestimate of the area between 0, and really in this case we're only getting an estimate of the area between 0 and 2. And the lower sum is an underestimate from 0 to 2. All right, because we stop our rectangles as soon as the first corner touches the function, so we get this empty space. So if we add up these rectangles, it's going to give us an estimate of this area underneath the parabola, but it's going to be less than the true area. All right, and hopefully it's obvious to you that the more rectangles we use, the more partitions we used, the more accurate our estimate would become. All right, so the area that we want to find between 0 and 2 underneath this parabola is approximately equal to the area of these 4 rectangles added up. Right? So in the first example, we want to use the upper and lower sums to approximate the area of the region using the subintervals shown above. And so we have 1, 2, 3, 4 subintervals. And it turns out in this case they're each exactly a half unit across. Right? So in this case, each rectangle has a width of 1/2. The rectangles won't always have a uniform width. And that's okay. We can just calculate the height times the width of each rectangle and add them up. That's all we're doing. So for the upper sum, the width is 1/2 for the first rectangle, and then the height of that rectangle for the upper sum, I'm going to kind of come up here, is defined by the height of the function at x equals 0. That rectangle tops out at f of 0, so that's the height. The next rectangle is the width of 1/2, and it is defined, the top of the rectangle is defined by f of 0.5. The next rectangle is 1/2. Its height is defined by the function at x equals 1, so we use f of 1, and so on. Right? We can calculate those. We can estimate them by looking at the graph, but we really can't calculate those values unless we look at f of x equals negative x squared plus 5. We plug in x equals 0, find that it's 5. We plug in x equals 0.5, we get 4.75, and so on. So the way that we get these actual heights is not necessarily from the graph, but by using the function that we were given. Right? If we weren't given a function, then we would have to just use the graph and estimate it. But since we do have the function, we want to get those exact values. The lower sum, now the definition of the heights of these rectangles is different. If you look up at the lower sum, the width is still 1/2, but now the height of that rectangle is defined by the function value at x equals 0.5. Right, the second rectangle is the width of 1/2, and its height is defined by the function value at x equals 1, and so on. So the difference between the way that these heights of the rectangles are defined is very important. So pause the video if you need to and think about that a little bit. Make sure it's clear to you why each of those is what it is. And once we do that, we can just, again, calculate f of 0.5, calculate f of 1, calculate f of 1.5, and calculate f of 2, and add those rectangles. So you can see that the upper sum and the lower sum, we know that the true area that we are looking for is somewhere in between 6.25 and 8.25. Here we have an overestimate, here we have an underestimate. So at the very least we have sort of a bracketed range where our true area could be. And again, if we used more partitions, we would get a better estimate, and that would shrink down the range of possibilities that we could have as that true area.